We've been talking about acids and bases, and as I showed you earlier, water is amphoteric. Just like an amphibian can live in the water or it can live on land, water can act as an acid or a base. And even in pure water, the water molecules do this, and they act as an acid and base with themselves. And so we get something like this. One water molecule acting as an acid, which is a proton donor, donating a proton to another water molecule, the proton acceptor, which is acting as a base. And the result is hydronium ion and hydroxide ion. Now, you might say, well, why would water do that? That just doesn't seem like something we would expect to happen. And we wouldn't. And it doesn't do this very much. This is an equilibrium, right? We've already done chapter 15. We know about equilibrium. In an equilibrium, it's going both ways. And just because some of this happens does not mean that all of the water turns into hydronium and hydroxide ion. In fact, it's mostly water molecules and only a little bit of the ions. But this is called self-ionization because water is ionizing itself. So it occurs to a very, very small extent. And we learned about equilibrium constants, and we learned when we were looking at solubilities. Let's just go back to this equation. When this occurs, we're going to get one hydronium ion and one hydroxide ion. The number of hydronium ions and hydroxide ions will always be equal. Just like when you have something like, here, let me draw on here. Get a better color. If you've got something like sodium chloride dissolving in water, you get sodium ion and chloride ion. All of the sodium ions came from the sodium chloride. And each sodium came with a chloride ion. This is like a pair of shoes, the left shoe and the right shoe. Doesn't matter how many pairs of shoes you have, when you take them apart, you have equal numbers of right and left shoes. Does that make sense? So with an ionic compound like this dissolving, where there's one cation and one anion, it's a 1-to-1 ratio, the number of sodium ions is always going to be equal to the number of chloride ions because they came in pairs. And the same thing is going on here. Two water molecules are one's going to act as an acid, one acts as a base. You're going to get equal numbers of hydronium and hydroxide ions. So the hydronium ion concentration is going to be equal to the hydroxide ion concentration, and that's going to be a small number. It's actually 1.0 times 10 to the minus 7th molar, moles per liter. That's at room temperature, 25 degrees Celsius. It's slightly different at other temperatures, but we're not going to worry about that. So, Kw, the equilibrium constant. I really need the equation on here. So, 2 H2Os is in equilibrium with hydronium ion and hydroxide ion. When we learned about equilibrium constant, we learned that it's the products times each other, their concentrations, divided by the reactant. But that solids and liquids are not included because their concentrations can't change. Because the concentration of a solid or of a liquid is just like its density. It's an intrinsic property. It doesn't matter how much of it there is, it doesn't change. So for this, K would equal the concentration of hydronium times the concentration of hydroxide. And that's what this is saying. Now, it's got this W for water, and it's called an ion product constant instead of a solubility product constant. We don't need to worry about those details. K is the equilibrium constant, hydronium ion times hydroxide, and that is going to be 10 to the minus 14. Because hydronium ion concentration is 1 times 10 to the minus 7, and the hydroxide ion concentration is 1 times 10 to the minus 7. And you multiply those together, and you get 1 times 10 to the minus 14. So this is an important relationship right here. This guy. Wait, that's not really what I meant to circle or box. This is the one we should remember. So in a neutral solution like pure water, hydronium is equal to hydroxide ion. Any questions? Nope. So in a neutral solution, those ion concentrations are equal. In an acidic solution, that means you've added acid to the solution. What do acids do? They release hydrogen ions. They release protons. They form hydronium ions. If the solution is acidic, then the concentration of the hydronium ion is higher. It's going to be larger than 10 to the minus 7. And if that's true, then the hydroxide ion concentration has to be less than 1 times 10 to the minus 7th. Because no matter whether it's acidic, basic, or neutral, these two concentrations, when you multiply them together, you always get the same number. That's why it's called an equilibrium constant. It doesn't change. The concentrations may change. This one might go up. If this one goes up, that one goes down. And when you multiply them together, you always get the same number. So if hydronium goes up, if it's greater than 10 to the minus 7, then hydroxide has to be less. In a basic solution, say you threw some sodium hydroxide in there. Bases form hydroxide ions in solution. So the hydronium ion concentration will be less than 10 to the minus 7, and the hydroxide ion concentration greater. Any questions? So this is a graph or an illustration from your book showing the relationship between hydronium and hydroxide ion concentration. So we often use red to symbolize acidic conditions and blue for basic. That's just kind of a convention. So here's neutral, right in the middle. Hydronium is 10 to the minus 7, hydroxide is 10 to the minus 7. As we go acidic and the hydronium ion concentration gets larger and larger and larger, then the hydroxide ion concentration has to get smaller. So let's just pick one of these. And let's just pick that one point there. Oops. So Kw equals 1 times 10 to the minus 14, and that equals hydronium times hydroxide concentrations. In that box that I made there with the red, what's the hydronium ion concentration? 10 to the negative third. And what's the hydroxide ion concentration? 10 to the negative 11th. And when I multiply those two numbers, what do I get? 10 to the minus 14. You can do that with any of these combinations. They'll always multiply and give you 10 to the minus 14. When one goes up, the other goes down. So if we know the concentration of one of these ions, we can calculate the concentration of the other one because we have this equation that relates them. So here they're asking us to calculate the hydronium ion concentration in each solution and then identify, is this acidic, basic, or neutral? So they're giving us a hydroxide ion concentration, and they're saying, what's the hydronium ion concentration? So the equation that we have is the KW one, and you don't really need the KW in there. So I'm just going to write the bare bones. Hydronium times hydroxide equals 1.0 times 10 to the minus 14. So I need to rearrange this equation and solve for hydronium ion concentration. So I'm going to divide by hydroxide on both sides. Because hydroxide over hydroxide is 1, we say that it cancels out. And so what we're left with here is that the hydronium ion concentration is equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration. So this is the equation that we need to take this hydroxide ion concentration to find out what the hydronium is. And these are also numbers that you're going to need to use scientific notation on your calculator because it can't handle 1 times 10 to the minus 14 otherwise. So I'm just going to write out the first one. So for A, I think it's A, yeah. We've got 1.0 times 10 to the minus 14, and we're dividing by this number, 1.5 times 10 to the minus 2. So 1 EE minus 14 divided by 1.5 EE minus 2 equals hydronium ion is, I'm getting 6.7 times 10 to the minus 13. Anybody else get that on your calculator? If you're not getting the right number, it's probably because you're using scientific notation, the EEEXP button on your calculator incorrectly. And please come and get some help with that. So, how about this one? Oh, we forgot. There's a second part, isn't there? Is it acidic, basic, or neutral? Well, in a neutral solution, both of these are 10 to the minus 7. Is the hydronium ion concentration greater than 10 to the minus 7 or less than 10 to the minus 7? It's less. So hydronium is less, hydroxide is more. Hydroxide is base, if this is a basic solution. So I'll write B for basic. Now this one, the hydroxide ion concentration is 10 to the minus 7. You can do the calculation, but if the hydroxide ion concentration is 10 to the minus 7, what does the hydronium ion concentration have to be? 10 to the minus 7. Because that's that neutral point, right? When they are equal at 10 to the minus 7, that's neutral. How about the one on the bottom here? You can't eyeball that one, so 1 EE minus 14 divided by 8.2 EE minus 10. (1.2 times 10 to the minus 5). Is this greater than or less than 10 to the minus 7? It's those pesky negative signs. 10 to the minus 5 is larger than 10 to the minus 7. Because 10 to the minus 5 is 0.1, 2, 3, 4. Well, it's not a 2, 1. That's 10 to the minus 5. 10 to the minus 7. 1, 2, 3, 4, 5, 6, 7. That's neutral solution. So which one's smaller? This one's smaller, this one's larger. So the hydronium ion concentration is higher than in neutral solution. So is it acidic, basic, or neutral? Acidic. Any questions? Yes?
Where did you get 1.2 times 10 to the negative 5?
I took, I used this equation here. I took the kW, 1.0 times 10 to the minus 14, and I divided by 8.2 times 10 to the minus 10. And that gives me 1.2 times 10 to the minus 5. And you can check your work by multiplying these two together, and you should get 1 times 10 to the minus 14. Any other questions? So this is a calculation that could very easily show up on the final exam. Hint, hint, hint. Was that subtle enough?